So let me spend a few minutes about the context of my work. It is about nickel titanium alloys. They are a unique class of material belonging to the Sgambitterra alloy systems. What is happening?
I think press something wrong.
Okay. Yeah. And these exploit unique shape recovery feature through two different properties, namely Sgambitterra effect and pseudoelasticity. Both properties are linked to a fully reversible solid state phase transition between two distinct crystal structures, the austenite, that is stable at high temperature, low stress, and the martensite. And this is called thermoelastic martensite transformation that can be activated either by temperature variation or by applied stress. So thanks to this feature, so the material have very special properties and coupled with very complex constitutive behavior that is characterized by marked nonlinearities, hysteresis, and marked mechanical coupling. And in particular, when the material is in its austenitic state, that is at high temperature, the material exhibits the so-called pseudoelasticity. It is a very large strain recovery capability. It is a kind of superelastic effect. And it means that if you start from the austenitic structure, the austenite is transformed into martensite monoloading, and this transformation is fully reversible monoloading, resulting in a very large strain recovery. On the other side, the Sgambitterra effect is a property of the material in its martensite condition. So if you start from the martensite state of the material at low temperature, the material is, if stress is applied, the material transforms, the martensite transforms in an oriented martensite, from twined to the twined martensite. And on unloading, you have a kind of pseudoplastic deformation that can be recovered by heating to the austenitic state. So this is a very complex feature, and it is also well known and well accepted by the scientific community that the local nature of this transformation phenomena has a very dominant, a very important role on material damage occurring under both static and fatigue loading conditions. That's exactly the motivation of our work. We want to study the effect of this local transformation phenomena on the fatigue and fracture properties of Sgambitterra alloys. So to this end, we are using fracture mechanics-based approach, and as you can, as we're known, they are very interesting when dealing with large cracks. I mean, when the crack size is much larger than the typical microstructural details, the grain size of the material. And this is even more interesting if considering the increasing number of industrial engineering application of Sgambitterra alloys. So we start from miniaturized components, mainly in the medical sector, to very large components. So I would like to mention one of them. This is a project in cooperation with the European Organization for Nuclear Research in Geneva and my research group that is about the development of bulk NT to develop couplers, pipe couplers with very interesting sealing capabilities to be used for the coupling the beam pipe of the particle accelerator at CERN. So within this context, however, we can say that standard solid theories cannot, solid mechanics theories cannot be directly applied to predict the fatigue and fracture properties of Sgambitterra alloys, mainly due to this stress and thermal induced transformation occurring in the crack tip region, and to the localized nature of phase transition mechanism. That's why we have, I'm sorry. That's why we have to develop local experimental approaches, special methods ranging from atomic simulation to microscale and to continuum scale. So let me start with the technical content of the presentation. I will talk about quickly fatigue and fracture properties of Sgambitterra alloy, then material experiments, and I will describe quickly a model we have developed, and then results, discussion, and conclusions. As I said before, the near crack tip stress-induced transformation occurring in the crack tip region cause significant redistribution of stress in the crack tip region that have a very important role. It is widely accepted by the scientific community, a very important role on both fracture and static properties of shear mineral. So this transformation mechanism can be due either to stress-induced martensite in the case of pseudoelastic material, or martensite orientation in the case of shear memory materials. So to this aim, we used two different types of material, both conventional materials. Pseudoelastic material, a material having austeritic structure at room temperature, the martensitic material, that is a material having a martensitic structure at room temperature. And in addition, to analyze the effects of thermomechanical coupling, we have analyzed the pseudoelastic material at increasing values of the temperature, between 25 and 65 degrees. And as you can see, there is a marked effect of the temperature. The critical stress transformation, stress-induced transformation, increases with increasing the temperature. And this is exactly what we have studied. And to this aim, we used single-edge crack samples that were obtained from nickel titanium sheets with thickness 0.5 millimeters for both fracture and plating experiments. So we are using different full field and local investigation techniques, including digital image correlation to capture local deformation in the crack tip, local strain, infrared thermography to estimate, to capture the local temperature variation due to stress and thermal-induced transformation in the crack tip region. But we have also developed a very special method based on instrumented nanoindentation that is able to capture very localized transformation phenomena, as you can see here in the crack tip region. So, in my presentation, I will focus more time constraint to results relative to digital image correlation. So we developed some special procedures that use displacement data obtained and captured by the AC to estimate the effective stress intensity factor by regression by using the Williams expansion series. And some results. We developed both linear and non-linear regression methods, and by this method we are able to capture, we are able to capture both the stress-induced transformation phenomena as well as the full strain and stress distribution. So a few words about the model we have developed. It's modified, it's a simple analytical model that is based on a modified Gillis correction of the linear financial mechanics. The model is basically based on the use of an effective crack length that takes into account that consider the nonlinear transformation region at the crack tip. And by the model, we are able to, it's based on an iterative approach, but we are able to define, to estimate the wall stress distribution, the transformation, the crack tip transformation, crack tip transformation as well. But we have also developed a possible fracture control parameters and stress intensity factor that is considering this unique unusual stress distribution. So let me show quickly the results. These are the results obtained from DIC measurements, the geometric correlation. In particular, there is a comparison between the upper figure are for type S. Type S is the pseudoelastic material, the material that has austerity structure at room temperature. The bottom ones are for martensitic material, the material having a martensite structure at room temperature. And as you can see, we have a much larger stress-induced transformation in the type M material, the martensitic, compared with the type S pseudoelastic. And we have also observed a large difference in the fatigue properties. I mean, much higher fatigue life in type M alloy compared with type S. And we did also comparison between DIC and our analytical model in terms of transformation contours, and we obtained very good agreement. So these results summarize the effects of temperature on the pseudoelastic material. Strain maps are for two different crack lengths and for two different values of the temperature, 25 and 65 degrees. And as you can see, there is a marked effect of the temperature. I mean, the transformation region increases with decreasing the temperature due to the decreased value of the critical stress for martensite, stress-induced martensite. And we have also captured a marked effect of the temperature on the fatigue properties. I mean, crack propagation rate increases with decreasing the testing temperature. So we try to explain these results by looking at the crack tip transformation phenomena. If we deal with the austenitic material, the transformation, the stress-induced transformation from austenite to martensite occurring on loading, vanish on unloading. I mean, reverse transformation occurs, and this is a kind of superelastic effect. And this transformation is mainly affected by the temperature due to the variation of the critical stress with the temperature. But if we look at the martensitic material, they behave in a completely different way, because on unloading we have martensite orientations, but these martensite orientations do not vanish on unloading. I mean, it's a kind of pseudoplastic deformation. That's why we expect to have a kind of compression residual stress on unloading. And this is why we captured the better fatigue properties of martensitic material with respect to austenite. So this figure summarizes the results in terms of fatigue crack propagation curves, and in particular a comparison between pseudoelastic and chain memory materials. And as you can see, just to give you a few information, the black curves here, the black points are relative, are the one obtained from linear acid fracture mechanics, and as you can see, that it exceeded clearly two different slopes. But it's just an apparent phenomenon, because it is mainly due to the transformation region, transformation behavior, linear transformation, that is not taken into account by linear acid fracture mechanics. In fact, if we analyze the results obtained by DIC, but also by our analytical model, they lie on a straight line. So it means that they can be described by Paris law. And just to conclude, this figure reports the fatigue crack propagation curve of pseudoelastic material, and in particular the effects of temperature. Also in this case, we by using linear acid fracture mechanics, we see three different behaviors at the temperature 25, 45, and 60, 85 degrees. But if we compare the results by the DIC, they become the same results. I mean that our effective results can be actually used to define fracture control parameters that are temperature dependent. So this temperature dependence is just an apparent phenomenon, because standard methods do not take into account the stress variation caused by temperature thermomechanical coupling. Maybe just this conclusion. So we demonstrated that the linear acid fracture mechanics phase in predicting fracture and fatigue properties of chain memory alloys, and we developed these experimental and analytical methods that can be actually used to predict the fracture and fatigue properties. And as future works, we are working on the effects of loading frequency. That is expected to play a very important role to the thermomechanical coupling. We are also developing some energetic methods, and we are working on special tests involving complex thermomechanical loading path, including both thermally and stress and thermally induced transformations. Thank you.
Thank you very much.
Thank you, very nice, very interesting work. I'm curious, maybe I missed, but I didn't fully understand if your model was also predicting the fatigue crack growth curve, so can you predict the Paris law behavior? And if yes, how? I didn't understand very well that part.
The model you mean?
So I saw some experimental data, but I was wondering in the fatigue crack growth curves, so later on.
We use, the model is just a model to estimate the effective stress intensity factors. So we use the model to recalculate the stress intensity range that are fitted in the fatigue region. Yeah.
Okay, so how do you say how to extend the crack, or just a calibration with the I'm thinking if you, so you're not modeling explicitly a crack growing and making decisions based on that effective stress intensity factor, is it?
So we just consider the crack length, and at a given size of the crack length, we recalculate the stress intensity range.
Understood. Thank you.
Yes, please.
Yeah, along the same line a bit. So you use the Williams series to fit on your strain data from digital image correlation, right? The Williams series is an elastic description, right? So, but at your crack tip, you do have your shape, your phase transformation. So, I missed that part actually. How can you still just fit basically the Williams series onto like this material, which has of course much more complex material behavior?
What we do is to obviously the model has some limitation. I mean, if let's say the investigation windows is much larger than the transformation zone, so you are considering as an equivalent elastic material, and you are neglecting. So you are fitting the Williams series in the elastic region, that resulting in an effective crack length. I mean, okay. Similarly to elastic plastic material, the Irwin's correction is exactly the same. So you are neglecting what is actually happening at the very crack tip, and you are forcing the elastic solution to fit the data around, outside the crack tip.
But that means that the stress and intensity factor is the stress and intensity factor corresponding to the sort of like hypothetical material with a different crack length that would behave elastically, right? So,
exactly. If you look here, these are experimental results. So what we are doing, this is in this region we have transformation. We are fitting the results in this region, just outside. But this results in a kind of equivalent crack length that is larger than the physical one. So this is the correction we are using. So we are considering an effective crack length that is larger than the real one.
Okay.
That in such a way that it can be considered as an approach similarly to the Dugdale or Irwin's correction of linear elastic fraction mechanics.
Thanks.
Okay, let's thank again. So the next presentation is evaluation of fatigue parameters, estimation method with regard to a specific range of fatigue, live and relevant monotonic properties by Dr. Basson. Yes?
Thank you very much.
12 minutes for the presentation.
Yes. Can you just show how to pause?